Hi everyone. In the last class we have discussed about orthogonal projections. Today we are going to discuss about mutually orthogonal projections and their applications. Let us quickly recall. If P is a bounded operator defined on H with P square equal to P, then we call P as projection or idempotent. P is a projection plus this condition null space of P is orthogonal to range of P. So, this condition, with this condition we call the projection to be orthogonal projection. So, we have proved the following result. Let us take P to be a projection. Then the following are equivalent. P is orthogonal. Second one is P is positive. The third one is P is self-adjoint. Fourth one is P is normal. And the fifth equivalent condition is that norm of P equal to 1. We have seen that if P is a non-zero projection, then norm of P is bigger than or equal to 1, but when P is an orthogonal projection, norm is exactly equal to 1. Okay. So, these are the equivalent conditions and we have seen some examples also. Let us look at few more examples. Let us take on R3 define P1, P2, P3 from R3 into R3 given by P1 of x1, x2, x3. This is equal to x1 0 0, P2 of x1, x2, x3 equals to 0, x2, 0 and P3 of x1, x2, x3 equals to 0, 0, x3. So, this is for every x1, x2, x3 in R3. And we can see that this Pj square is Pj equal to Pj star for all j equal to 1, 2 and 3. That means all these projections are orthogonal, and if you look at the corresponding ranges, so we can easily see that range of Pj is span of Ej, j equal to 1, 2, 3. This E1 is 1, 0, 0, E2 is 0, 1, 0 and E3 is 0, 0, 1. This is a standard orthogonal basis for R3. And in this case, range of Pi is orthogonal to range of Pj for all Ij in this set 1, 2, 3 and I not equal to j. That means the ranges are mutually orthogonal for all these projections. Such projections we call as mutually orthogonal projections. So let us look at one more example. Define Pn from L2 into L2 by Pn of x1, x2, x3 so on is defined by 0, 0, 0. Nth component is xn, all remaining are 0. So this is for every xn in L2. We can easily show that Pn is an orthogonal projection. Verify that Pn star is Pn, that equal to Pn square for every n in n. This is easy to verify. And range of Pn, span of En, where we know that En is the set of all En, n in n is a standard orthogonal basis. So En is 0, 0, 1, 0. This is nth place. Now we can easily show that these Pn's are mutually orthogonal. Range of Pn is orthogonal to range of Pm for every mn in n, m not equal to n. So the conclusion is that they are mutually orthogonal. Let us try to define. Let us define. If you have a family of orthogonal projections, let P alpha is coming from a direct set lambda, be a family of orthogonal projections. Then P alpha is said to be a mutually orthogonal family of projections if you take any two projections in this family, they are mutually orthogonal. That means P alpha, so range of P alpha is orthogonal to range of P beta for all alpha beta in lambda, alpha not equal to beta. If such a condition holds true, then we can conclude that the family of projection is a mutually orthogonal family of projection. Okay, now we can ask what is the advantage of mutually orthogonal projections. So let us try to look at the advantages of such family of projections. Suppose you have two mutually orthogonal projections P and Q. Let me write as a proposition. The first question we can ask is that when we can say that given two orthogonal projections are mutually orthogonal. So let us take P and Q be orthogonal projections. Then the following are equivalent. The first one is range of P is orthogonal to range of Q. That means P and Q are mutually orthogonal. The second one is the product PQ is 0. So let us prove 1 implies 2. So we want to show that PQ is 0. That means for every x in H, we want to show that PQX is 0. Okay, so let us take x in H, then we can conclude that QX is in range of Q. So that is orthogonal to range of P. Hence we can say that PQX is 0 because QX is orthogonal to range of P. So that means range of Q is contained in range of P perp, that is null space of P star. Since P equal to P star, that is null space of P. Hence we can say that PQX is 0. So on the other hand, let us try to prove the other implication. If x is in range of P and y is in range of Q, we want to show that inner product x with y is 0 with the condition that PQ is 0. Then we can show that inner product of x with y is nothing but inner product px with qx, px with qy, because px equal to x and qy is y, because they are coming from ranges. So we can say that this is q p, or we can, so this we can write as x p q y. When we take p to the other side, we will get p star, but p star equal to p, and we know that pq is 0. So this implies that this inner product is 0. Hence inner product x with y is 0. So from this we can conclude that P is mutually orthogonal to Q if and only if PQ is 0. Okay, let us look at some more important observations. Let P and Q be two orthogonal projections. Such that PQ equal to QP, then we can say that PQ is an orthogonal projection with range of PQ is exactly range of P intersection range of Q. Okay, so product of two orthogonal projections is an orthogonal projection provided they commute with each other. So it is enough to show that PQ square equal to PQ, that equal to PQ star. So we have that PQ square is PQ, since Q commutes with P, so this is P square Q square, that is PQ. And if you look at PQ star, this is Q star P star. Since P and Q are orthogonal, they are self-adjoint, this is nothing but QP. So this is, since they commute, that is equal to PQ. So from these two conditions we can conclude that PQ is an orthogonal projection. Okay, now we want to decide the range of PQ. So to do this, observe that range of P range of PQ is contained in range of P, and range of QP is contained in range of Q. Since PQ equal to QP, so we get that range of PQ is contained in range of P intersection range of Q. Okay. On the other hand, so let us pick some element from intersection of these two ranges. Let us take y is in range of P intersection with range of Q. Then we can say that Py is y as well as Qy is also y. Okay. Then we want to show that y is in range of PQ. So if you look at PQy, this is Py because Qy is y. So again this is y since Py is y. So hence we can say that y is in range of PQ. So from these two inclusions we can conclude that range of PQ is exactly range of P intersection range of Q. Okay, so let us look at some more interesting properties of mutually orthogonal projections. So let us look at one more result. Let PQ be two orthogonal projections which are mutually orthogonal. Then we can show that P plus Q is an orthogonal projection with range of PQ, range of P plus Q as range of P direct sum with range of Q. This is orthogonal direct sum. Okay. So to show that it is an orthogonal projection, it is easy. P plus Q star is P star plus Q star, that equals to P plus Q, because P and Q are self adjoint because they are orthogonal. So if you look at P plus Q square, that is P plus Q into P plus Q, and if you multiply you will get P square plus PQ plus QP plus Q square, and you will get this is P plus Q because P square is P, Q square is Q, and we know that this is 0, and when this is 0 its adjoint is 0, that is QP is also 0. Okay. So from these two relations we can conclude that P plus Q is an orthogonal projection. Now to see the range of this projection, let us take y is in range of P plus Q. Then we can say that P plus Qy equals to y. That means y can be written as Py plus Qy. Now Py is in range of P and Qi is in range of Q, and we know that they are mutually orthogonal, so this Y is in range of P, orthogonal direct sum with range of Q. Now on the other hand, if you take Y equal to Y1 plus Y2, where Y1 is in range of P and Y2 is in range of Q, so then we can say that if you look at P plus QY, this is PY1 and plus PY2. PY2 is 0 because Y is coming from range of Q, that is part of null space of Q, null space of P. So this we can say that this is PY1 and that is QY1 plus QY2. Again QY1 is also 0 because Y1 is coming from range of P, and range of P is orthogonal to range of Q. So range of P is part of null space of Q, so you will get QY2, but this is Y1 plus Y2, so that is Y. So P plus QY is Y. That means Y is in range of P plus Q. So from these two relations we can conclude that range of P plus Q is exactly range of P plus range of Q, and we know that this direct sum is orthogonal because range of P and range of Q are orthogonal to each other. Okay, now this result we can extend to finitely many projections. So let me write as generalization. Let us take P1, P2, P and B mutually orthogonal, or we can say that orthogonal projections with Pi Pj is 0 for all ij equal to 1 to n and I not equal to j. When I equal to j, then that is Pi square, you will get Pi. Okay, then we can say that P1 plus P2 so on Pn is an orthogonal projection with range direct sum of range of Pj j equal to 1 to n. This can be done using the same way, using the same method that we proved for two projections. Let us prove the following result. Let P and Q be orthogonal projections then the following are equivalent. P minus Q is an orthogonal projection norm of Px is bigger than norm Qx for every x in H. Third one is range of P contains range of Q, and if you look at the product of projections PQ, then you will get the smaller projection Q. Here smaller means range of Q is contained in range of P. And the fifth one, QP equal to Q. So here we can say that P is bigger than or equal to Q, because P minus Q is an orthogonal position, means it is positive, hence P is bigger than or equal to Q. So let us look at the proof. 1 implies 2. So P bigger than or equal to Q implies inner product Px with x is always bigger than inner product of Qx with x for every x in H. So this implies, since P square equal to P and Q square equal to Q, we can say that in place of replace P replace by P square, and similarly for Q, and you take P to the other side, you will get P star, but P is orthogonal projection, P star equal to P. So from this we can say that norm Px square is bigger than or equal to norm Qx square for every x. Since all the terms involved here are positive, we can say that norm Px is bigger than norm Qx for every x in H. Now this implies this proves 1 implies 2. Let us look at 2 implies 3. If norm Px is bigger than or equal to norm Qx, we want to show that range of P is contains range of Q. Let us take y is in range of Q. Then we know that Q of y is y. So we want to show that Py is also equal to y. Hence norm of y, we can write norm Qy, and we know by hypothesis that this is less than norm Py, and P is a self-adjoint bounded operator whose norm less than or equal to 1. So we can say that, in fact, norm of P is 1, so this is norm y. So hence we can say, so norm of Py is norm y, or we can say that norm of Py square is norm y square. So again you can write that as inner product of Py with Py, on the right hand side inner product y with y. So if you simplify, you will get I minus Py with inner product y is 0, or we can say that I minus P is also an orthogonal projection. So I minus P star equal to I minus P, that equal to I minus P square. So we can use the same trick that we used earlier. From that we can conclude that inner product of I minus P with itself is 0. So that is nothing but norm of I minus Py is 0. So that means we can say that Py equal to y. So we have shown that y is in range of Q. So this is, and we have taken y is in range of Q, and we have shown y in range of P. So range of Q is contained in range of P. Now 3 implies 4. Assume range of Q is contained in range of P. Then we have look at PQ at x, that is P of Qx. Now Qx is in range of Q, that is part of range of P. So we take any element of range of P, then P of that element is itself. So this is nothing but Qx. So that implies that PQ equal to Q. Now 4 implies 5 is trivial. So PQ equal to Q. PQ star is Q star, and this implies Q star, P star is Q star, P star is Q star, but all are self-adjoint. So QP is exactly Q. Now to show 5 implies 1, assume that qp equal to q, then we have we want to show that p minus q is an orthogonal projection. First let us look at that it's a projection or not. P minus q square is p minus q multiplied by itself. It is p square minus pq minus qp plus q square. We know that qp is q, and similarly pq is also q. So this implies p minus q plus q. So this is p minus q. So p minus q is a idempotent or projection, and we also know that p minus q star is p star minus q star, that is nothing but p minus q. Hence therefore p minus q is bigger than or equal to 0. It's an orthogonal projection. Now this implies phi implies 1. Okay, this theorem gives a relation between two projections having the condition range of one projection is contained in range of the other projection. So if you take the multiplication of product of such projections, we get the smallest projection. Okay, now let us look at the range of p minus q. We only conclude that p minus q is an orthogonal projection. So let us look at, so we have, so if p minus q is an orthogonal projection, then we can say that range of p minus q, we can write range of p minus q can be written as pq. This is range of p into I minus q. So we know that range of pq is range of p intersection range of q. Here in place of q we are replacing I minus q. So this is range of p intersection range of I minus q. This is nothing but range of p intersection range of I minus q is null space of q, but null space of q is orthogonal complement of range of q. So next we discuss about operator matrices. Let us take two Hilbert spaces. Both are complex. So we know that H is the direct sum of H1 and H2. This is an inner product provided if you define X as X1 X2 and Y as Y1 A2. Then the inner product we have already defined as inner product of X1 Y1 in the first Hilbert space and inner product of X2 Y2 in the second Hilbert space. We know that this is inner product space. In fact, since H1 and H2 are Hilbert spaces, we can conclude that H is also Hilbert space. Now let us look at a bounded operator defined on H. So then we can write T as a matrix whose entries are operators T11, T12, T21, T22 here. Here this is H1, H2, this is H1, H2. We can say that this Tij is a map from Hj into Hi, I equal to 1 to 2, which is linear unbounded. In fact, we can get what is Tij when T is given. So okay, so here if I take X as X1, X2, in H, then T of X we can define as T11, T12, T21, T22, X1, X2. So this is nothing but T11 X1 plus T12 X2. This is T21 X1 plus T22 X2. In other words, so we can treat this as a matrix and work as in the usual matrix case. Okay. Here when I say Tij, it's a map from Hj to Hi. For example, if you take T11, that is H1 to H1, and T22 is a map from H2 to H2. So here if you look at T11, so this is domain, this is codomain. So T11 is a map from H1 into, so this domain and this codomain. Similarly, T21 is a map from H1 and taking values in H2. So T21 is a map from H1 into H2. So T12 is a map from H2 to H1. Okay. Now on the other hand, suppose in this case actually we can get what is T11, what is T12, T21 and T22 using projections. Let us take projections. Let P1, so let us take Pj from H to H be an orthogonal projection with range of P, range of Pj is exactly Hj. That means now P1 is a map from H into H, and range of Pj is, range of P1 is H1. So that means P1 of X1, X2 is nothing but X1 comma 0. P2 of X1, X2 is 0 comma X2, where X1 is coming from H1 and X2 is coming from H2. Now if you look at Pi, if I want to find T11, now T11 is a map from H1 into H1. Now T11 we want to find from T. So consider P1 T P1 at X1 X2 is nothing but P1 T. P1 of X1 X2 is X1 comma 0. Now this is P1 of T of X1 comma 0, that is T11 X1 T21. So this is T11 X1 T21 X1. Now if you look at this, you will get T11 of X1 by definition 0. Now if you don't want second component, X2 component, then we get T11 at X1. So X1 is an element from H1. So if you look at P1 T P1 restricted to H1, so we know that X1 is coming from H1. We know that H1 is subset of H1 direct sum 0, which is subset of H1 direct sum H2. So we have already noted this. H1 can be embedded in H1 direct sum H2 in this way. So when we look at P1 T P1 restricted to H1, that means if you look at only x1, then this is exactly t11. Similarly, if you want to compute tij, we can say that this is pi tpj restricted to hj. Now this is a map from hj into range of pi, that is hi. If T is a linear map from Cn to Cm, then we get an m by n matrix corresponding to it. Similarly, if we have a map from Hj to Hi, you will get Tij here. So that means given any bounded operator on direct sum of two Hilbert spaces, we can actually write in this matrix form. Now on the other hand, suppose we have Tij from Bhj to Hi, where ij equal to 1 to 2, then we can define a map from T from H to H by this matrix T as T11, T12, T21, T22. So this is a map from H into H. So in fact, we can show that when if T is Tij is bounded, just by looking at the definition of bounded operator, we can show that T is bounded and norm of T is less than summation ij equal to 1 to 2 norm of Tij square whole power 1 by 2. That means we can show that T is a bounded operator. When T is a bounded operator, the Tij's are given in terms of the projections Pi, T, Pj, hence it is bounded. So given 4 bounded operators Tij, we can construct a bounded operator T, and given any bounded operator T, we can actually generate 4 bounded operators Tij in this way. Now the advantage of this is the following, that we can actually treat this as a matrix. In fact, elements in this matrix are operators. So this is known as operator matrix. So we can actually take the product and sums of two operator matrices as usual, the way we take for n by n complex matrix or m by n complex matrix. Okay, so if S is S11, S12, S21, S22 with the same decomposition H1, H2, H1, H2, then we can say that S plus T can be written as S11 plus T11, S12 plus T12, S21 plus T21, S22 plus T22. This component wise addition, and St can be written as the product of two matrices in the usual way. This is S11, S12, S21, S22 multiplied by T11, T12, T21, T22. This is the usual matrix multiplication. This is S11, T11 plus S12, T21, S11, T12 plus S12, T2. The third element is S21, T11 plus S22, T21. Fourth one is S21, T12 plus ST2, S22 multiplied by T22. Okay. Then T star is nothing but similar to the adjoint of a complex matrix. This is T11 star, T21 star, T12 star, and T22 star. So these are the operations we can have on Mn of, I am repeating, these are the operations we can have on B of H1 direct sum H2. Now if T is T1 0 0 T2, then in this case this is H1, this is H2, this is H1 and this is H2. We can say that T of x1 x2 is nothing but T1 x1 comma T2 x2. So this can be written as saying that T can be written as T1 direct sum of T2, because T1 x1 comma T2 x2, this is nothing but direct sum of T1 x1 plus T2 x2. This is direct sum of, so this is the way we write direct sum of two operators. If the off diagonal entries in this operator matrix are 0, we can say that T is nothing but direct sum of the first operator and the second operator. Looking at the properties of T, T1 and T2, we can actually get properties of T. For example, we can say that T is invertible if and only if both T1 and T2 are invertible. T is 1 1 if and only if T1 and T2 are 1 1 if and only if T is 1 1. Range of T is closed if and only if range of T1 and range of T2 is closed. And we can actually get many more properties from T1 and T2. That means T can be analyzed using the properties of T1 and T2 and vice versa. Okay, so we'll stop here. Thank you.